everyone, this is Babitha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering. In this session, I am going to discuss about the different capacitors which are existing in the hybrid pi model and also the short circuit current gain of the hybrid pi model. So while coming to the contents here, I am going to revise few points related to the hybrid pi model, whatever we discussed in the last session, and also what are the conductances we derived in the previous session. And next I'm going to discuss about the capacitors which are existing in the hybrid pi model and common emitter short circuit current gain of the pi model. So before going to the different capacitors which are existing in the hybrid pi model, just I'll revise the hybrid pi model here. Actually, why we are moving for this hybrid pi model here? Even though we are having the H parameter model that is applicable for low frequency signals, and these H parameter values are also varying for different frequencies, and the values are different for different frequencies. And if we take two similar transistors also, we may get different H parameter values. So because of that reason, in order to do the analysis in the H parameter model, it is difficulty. That's why we went for the approximate model also. In the approximate model, we removed the two H parameters, that is reverse voltage gain as well as output admittance parameters we removed in the approximate model of the hybrid model. But this hybrid model is applicable for low frequency signals and it is varying for different frequency signals. So that's why we need to check the operation of the transistor at different frequency levels. So in order to see the performance of the transistor at different frequency levels, we went for the hybrid pi model. So what is the basic difference between the H parameter model and hybrid pi model? Here it is. For that I consider the H parameter model and hybrid pi model. This is hybrid pi model of the common emitter circuit. Okay, so in this case, this H parameter model we implemented between the base, collector and emitter terminals of the transistor, and we are having the four parameters: input impedance HIE, reverse voltage gain HRE, forward current gain HFE, and output admittance HOE. So in the small signal analysis, we derived these four parameters, and after deriving these four parameters, we implemented this H parameter model. So from this H parameter model, we can able to do the small signal analysis of the transistor. That is nothing but from that small signal analysis, we can able to find the transistor or amplifier parameters. Those are input impedance, output impedance, as well as voltage gain and current gain parameters. In terms of these H parameters, we derived already. And I have mentioned already all these parameter calculations are applicable for the low frequency signals, and to get it in the high frequency signals also, we are moving for this hybrid pi model. So what is the basic difference between H parameter model and hybrid pi model? Means in the case of hybrid pi model, the extra terminal B dash is included in the amplifier circuit. Along with this base, collector and emitter terminals, the one more extra terminal B dash is adding to the circuit. So this B dash terminal is not visible to us. It is internally present in the transistor itself. But because of presenting this B dash terminal in the high frequency model, this B dash terminal is spreading different resistances to the different terminals which are present in the amplifier circuit. So because of this, we are getting extra resistance, that is RB B dash, between base spread resistance and base terminal, and between base spread resistance and collector also we are existing one more resistance, that is RV-C. And between base spread resistance and emitter terminal also we are getting one more resistance, that is RV-E. And between output terminal collector and between emitter terminal also we are existing the one more resistor, that is RC. So because of adding one extra terminal, different resistances are spreading in the circuit, so that in the case of hybrid pi model, that's why we have calculated all these conductances related to all these four resistors. 1, 2, 3 and 4 resistors. So these four conductances related to these four resistances as well as the output conductance GM. These parameters we derived in the last session. So along with these conductances and resistances, the capacitors are also included in the high frequency model. Why capacitors are included here means the reactance of the capacitor, here it is 1 by 2 pi Fc. So for low frequency signals, the frequency value is less means the reactance value is very high. So once the reactance is very high means the capacitor takes very less signal, very less AC signal. So in that case we are taking here it as short circuit. The capacitors are taking as a short circuited in the case of H parameter model. Why? Because it is meant for low frequency signals. But as frequency is increasing, the reactance of the capacitor is decreasing here. So once the reactance of the capacitor is decreasing means the resistance level of the capacitor is decreasing. That is nothing but the overall capacitance value is increasing here. So the capacitance value is increasing in the case of high frequency signals. So that's why we are including the capacitors in the analysis part of the hybrid pi model. So here we have two capacitors between base spread terminal and the collector, that is CC, and between base spread terminal and emitter one more capacitor, that is C. So in the previous session we derived the GB-C conductance related to the first resistor and GB-E conductance that is related to the second resistor and GB-C conductance that is related to the third resistance and GCE related to the fourth resistance and the GM output conductance. So these all parameter derivations we have discussed already. So in this session I am going to discuss about the different capacitors which are existing in the hybrid pi model, and along with that how much current gain we are getting in the case of hybrid pi model. So in the capacitance, in the case of hybrid pi model, we are having two types of capacitances, that is diffusion capacitance and transition capacitance. Generally, in the case of diode circuits also, we discussed this type of capacitances. In the case of diode, when it is forward biased, we will get the diffusion capacitance. And when the diode is in reverse bias condition, then we will get the transition capacitance. And always the capacitance of the capacitor is inversely proportional to the depletion region of that particular junction here. So if the junction is or PN junction diode is in forward bias condition, in that case the depletion region width is very less. And when the diode is in reverse bias condition, the depletion region width is very high. And once the depletion region width is very high means, in that case the capacitance value is very less. And the depletion region width is very less means the capacitance value is very high. So from this analysis we can say the value of diffusion capacitance is very high compared to the value of transition capacitance. Why? Because diffusion capacitance is existing in the forward biased case and transition capacitance is existing in the reverse biased case. And we can represent this diffusion capacitance as CD or C simply, or transition capacitance we can represent here it as CD or C. So now first we'll discuss about this diffusion capacitance CD or C. Okay. So generally this diffusion capacitance is sum of the two capacitances in the circuit here, that is the diffusion capacitance CDE as well as the emitter junction capacitance CT. So that is the sum of two capacitances. But here for the forward biased emitter junction, CDE value is very high compared to the CTE value. Why? Because I have already mentioned it is the forward biased capacitance and this one is the reverse biased capacitance. So that's why the value of CDE is very high compared to the CTE. So that I can make it as CE is approximately equivalent to the highest capacitance, that is CDE. Okay, so this CDE value is directly proportional to the how much current which is flowing in the emitter terminal of the amplifier or transistor, but it is not dependent on the temperature. If you are increasing or decreasing the temperature value also, there is no variation in this particular capacitance, but if you vary the emitter current, there is a change in the diffusion capacitance CD. So this diffusion capacitance we can represent in the transistor. For that purpose, I am considering the PNP transistor here. Okay, this PNP transistor is in now forward biased condition. So when we can make it as forward biased condition means P is nothing but the positive, or it is having majority carriers are holes. So holes are having positive charge. So that's why the positive terminal of the battery is connected to the P region here and the negative terminal of the battery is connected to the N region here. Okay. This voltage generally we will call it as VBE voltage or supply voltage. And this collector terminal is again P region and base terminal is N region. So here in this case, this side, output side, we need to provide the reverse bias. So that's why for the P region, we are connecting the negative terminal of the battery. And in this side, we are connecting the positive terminal of the battery. So this voltage, we can call it as VCE voltage. So that we can say our transistor is in now active region. That is nothing but emitter base junction is forward biased and the collector base junction is reverse bias. So that only we can say our transistor is operating in amplifier mode. Once we are connecting in the active region of operation means, so that we can say our transistor is operating in the amplifier mode. So when we are connecting the transistor in the amplifier mode, the input junction, that is emitter base junction, is forward biased. So in that forward biased emitter base junction, there is a existence of this diffusion capacitance C. So generally we are calling it a C, but in the hybrid pi model, it is existing between the base spread terminal as well as emitter terminal. So that's why we can also call it as CB-E. So here the emitter terminal acts like one plate of the capacitor and the base terminal acts like one more plate of the capacitor, and in between that the junction or this one acts like a dielectric medium of that capacitor. So this dielectric medium width is depends upon the depletion region width of this emitter base junction, and that depletion region width is depends upon how much voltage you are providing to this emitter base junction. If this voltage is less means the depletion region width is more, and if this voltage is very high means this depletion region width is very less. And accordingly, the capacitance value will also increasing or decreasing. Okay. So as I have already mentioned, once this emitter base junction is forward biased, we will get this diffusion capacitance CB-E or C capacitance. So now we will see the derivation of this diffusion capacitance. So for that, we are taking the forward biased condition of the emitter base junction here. Once we are applying the forward bias to the emitter base junction, the depletion region width is less here. The depletion region width is less means the number of charge carriers are accumulating near the plates are very high. So the density of the charge carriers are very high near the junction, and if the carriers are moving away from the junction means the density of the charge carriers will be reduces here. So the charge stored on both sides of the junction and varies with the applied external voltage VB. So that we are representing with the graph here. For that, I am considering only the base region here between the emitter and collector. I am considering only the base region. That is nothing but how much charge gradient or charge carriers are present from emitter to collector. How the charge carriers are decreasing once you are varying the applied voltage to the emitter base junction here. So this figure represents the injected hole concentration versus distance between the base region of PNP transistor. So here the base width we are taking here it as W, okay, and the base width is always very less. Why? Because it is very lightly doped and area of this one also very less. So that's why the width of the base is also very less. So here the collector junction is reverse biased and emitter junction is forward biased. So that's why across the emitter junction the charge carriers are high, very high here, and once it is reaching from emitter to base to the collector, the density of the charge carriers will become zero here. Why? Because of reverse bias applying to the collector junction. So because of the charge carrier movement only, the charge will develop in the base, that we are representing here it as QB. So this QB value is very high at emitter base junction and it is very low or almost zero in the case of collector base junction. So that value we are representing with P dash of 0. So suppose the length of the base is very less compared to the LB. In that case, the P dash varies almost linearly from the P dash of 0 to 0. That we can observe in this particular diagram. So how much charge is stored in the base terminal? That we are representing with the total charge carriers P dash of 0 divided by 2 into A into W into Q here. Why we are taking here it as P dash of 0 by 2 means these charge carriers are distributed between the emitter base junction as well as collector base junction. So that's why we are taking here it as half P naught of 0 by 2. So what are all these values? Here P naught of 0 by 2 is average concentration across both the junctions. And A is nothing but the cross-sectional area of the base terminal, and area into width is nothing but the volume of base terminal, and Q is the how much electronic charge which is stored in the base terminal. So this, from this relation we can write P dash of 0 is equal to this 2. If we take it as left side, 2 multiplied with QB if we take these terms also left side, we will get it as 2QB by AWQ. That is our P naught of 0 value. And also this diffusion capacitance is directly proportional to the diffusion current or emitter current here. So that's why I am equating this diffusion capacitance value or charge developed in the base terminal to the current I here. Current I equal to A into Q into dB into dP by dx here, where dB is nothing but diffusion constant, that is nothing but with how much force the charge carriers are diffusing towards opposite terminals or towards opposite regions here. dP is nothing but difference of concentration of charge carriers. So at the collector terminal, the concentration is very high, that is P dash of 0, and across the output terminal, that value is 0. So that's why we are taking the difference of the two charge carrier concentration. And dP, the differentiation of this one, we will get it as P dash of 0. And dx is nothing but the width. So here we can write this equation as, after substituting these two values, we will get it as AQ dB into P dash of 0 divided by W. So that thing only I am considering again here. I equal to AQ dB into P dash of 0 by W. So from this we can write again P dash of 0 equal to 2QB by AWQ. This value we have already derived from the diagram. And here I equal to what we will get if you substitute this P dash of 0 value in the I equation. We will get it as I equal to AQ dB into P dash of 0 divided by W. So if you substitute P dash of 0 value here, means you will get it as AQ dB into 2QB divided by AWQ into W. So this A and A double Q and Q will get cancelled. So the remaining values are 2QB dB divided by W square. So this, from this we can write the charge in the base region, that is QB is equal to W square into I divided by 2dB. This is the total charge which is developed in the base terminal. Why we calculated this particular charge developed in the base terminal means, by using this charge developed in the base terminal only, we can able to find the capacitance value in the base emitter junction, that is diffusion capacitance. Okay. So the static emitter diffusion capacitance is given by the rate of change of charge with respect to the emitter voltage V. So that QB we are using here. So CD equal to dQB by dV, that is equal to W square by 2dB into dI by dV here. That is nothing but for the QB we are performing the differentiation. So here the differentiation of I by V is nothing but RE. RE equal to V by I, resistance in the emitter terminal equal to voltage by current. So that's, here we have I by V. So that's why we are replacing it with 1 by RE. So here 1 by RE, or RE is nothing but the emitter junction incremental resistance. So now we can write CD equal to W square by 2dB into IE by VT. So here IE by VT is nothing but, again it is the transconductance GM. This we derived in the previous session. So which indicates that the diffusion capacitance is directly proportional to the emitter current here. But experimentally we can say CE we can determine from a measurement of FT, that is transition frequency. So the frequency at which the CE short circuit gain is drops to unity. That is nothing but where the gain is getting it as 1. At that time, how much frequency we are getting, that we are indicating with the ft. So at that particular frequency ft, we will get the capacitance as gm by 2 pi ft. So this is the total value of the diffusion capacitance in the forward biased emitter base junction. And next type of capacitance is transition capacitance. So this transition capacitance will exist in the reverse biased collector base junction. So that's why we are representing it at the collector base junction. So this is emitter, this is base, and this is collector. So between collector and base, we will get this transition capacitance Cc. So always this collector base junction is reverse biased and emitter base junction is forward biased. I have already mentioned, though it is reverse biased junction, so this capacitance value is very less. And the value of this capacitance is always depends upon the depletion region width here. So if you increase the more reverse voltage, the depletion region width will be also very high, so that the capacitance Cc value will be very less. And the reverse bias voltage is decreasing means the depletion region width is also decreases, so that the Cc capacitance will increase here. So this Cc capacitance we can also represent here it as Cb dash C. Why? Because it is existing between B dash and C. So that's why I can represent here it as Cc or Cb dash C. And always Ce is far greater than Cc in any kind of diodes or transistors or amplifier circuits. So now we will see the derivation for this transition capacitance. So this transition capacitance is inversely proportional to the applied collector to base voltage. So that's why we are indicating here it as Cc proportional to 1 by Cb power n. Here n is nothing but abrupt junction, and if n is equal to 1 by 2 is for abrupt junction and 1 by 3 for graded junction. So we can approximate this transition capacitance as epsilon A by W here. So what is mean by this abrupt junction and graded junction? We'll see now. So abrupt junction means when the depletion region or space charge layer is terminating or decreasing when you are applying the voltage to the semiconductor diode. At that time, you will get the constant impurity concentration. So at that particular point, how much the capacitance voltage characteristics we will get, that we are representing with the abrupt junction capacitance or abrupt junction characteristics. And similarly, the graded junction transistor is nothing but it is a type of high speed bipolar junction transistor. It is having a doping electric field is less compared to, that is nothing but the doping level is very less in the base, so that the base transition time is also very less. In that case, we can say it as the graded transistor type of junction. So till now we have seen the two capacitances which are existing in the hybrid pi model. So now we will see the validity of this hybrid pi model, where we can utilize at what frequencies we can utilize. So for that, these hybrid pi equivalent network elements are frequency dependent. So that's why we are considering it as CD equal to 2 pi f into W square by 6 dB, and which is almost less than 1. Here I have already mentioned W is nothing but base width, dB is nothing but the diffusion constant, and f is the input signal frequency. So from this analysis only we have calculated two capacitances. Those values are Gm W square by 2 dB and C equal to Gm 2 pi f. So from these two capacitances, we can write it as this W square by 2 dB term. From these two relations, we can write it as W square by 6 dB. Okay, and this one I can write it as C by 3 gm. So here this value is equivalent to pi ft. 2 pi ft gm is we are taking across 2 pi ft. So that's why we are getting it as 1 by 6 pi ft. So now in this case, our equation 1 will become, this equation 1 will become less than 1. So in this case, I am substituting the value of W square by 6 dB. What is that value? W square by 6 dB value is 1 by 6 pi ft. So 2 pi f into 1 by 6 pi ft is less than 1. So here 2, 3 of pi will get cancelled. So from this we can write frequency should be far less than 3 ft. So for the hybrid pi model, it is valid for frequencies up to equivalent to ft by 3 only. It can access the signal till transition frequency by 3 range only. So next we need to calculate the parameter short circuit current gain. So in order to find that short circuit current gain, here we require the concept called Miller's theorem. So what it indicates, generally Miller's theorem is used to convert one type of resistance which is present in one type of circuit into, it is representing in different form in same circuit. One resistance which is existing one type in same circuit, that we are representing in different way in the same circuit. Okay, so for example, I am taking this 2-port network with the 2 ports, port 1 and port 2. At port 1 we are having the input voltage Vi and the output voltage V0. So between these 2 ports we are having the impedance Z. So this impedance Z I am representing, or I am dividing into 2 impedances in the same circuit. That is nothing but this Z I am dividing it into Z1 and Z2. That is nothing but the impedance especially for input port as well as the impedance especially for output port. So that's why this first divided impedance we are representing in the first port, that is port 1 to ground, and the second impedance we are representing at port 2 and ground. So in order to divide this total resistance into 2 values, we are having some room. So for that I am taking the impedance connected between nodes 1 and 2. So it is replaced by 2 impedances Z1 and Z2. So Z1 is connected between the 1 and ground, Z2 is connected between the 2 and ground. Okay, so here Vin and V0 are the voltages at node 1 and node 2. So the values of Z1 and Z2 can be derived from the ratio, that is output voltage by input voltage. That ratio we are taking it as K. So here we divided the total resistance into 2 resistances Z1 and Z2. So that Z1 value I can represent here it as Z by 1 minus K, and the second impedance Z2 I can represent here it as Z into K by K minus 1. So how we got these 2 particular values, we will see. So from the statement of Miller's theorem, we can say the effect of impedance Z on the input circuit is a ratio of V into current I, which flows from input circuit to output circuit. Okay, so how we can prove this one means Z1 is equal to V in by I here. So for that I am taking 2 ports again in the input. So input side we are having V in, output side we are having V out. Okay, so this is the total impedance, but at the input side we are representing it as Z1. So to calculate this Z1 from input side I am looking. So when I am looking into the input side, my input input impedance is V in by I in the circuit. So that's why V in by I. But what is my I which is flowing in the circuit? That is the difference of these two voltages, V in minus V naught divided by the total impedance Z. So that's why I equal to V in minus V naught by Z. So this I value substitute in the Z1. So if you substitute in the Z1, we will get it as V in by V in minus V naught into Z. And here take V in common in the denominator. If you take V in common in the denominator, we will get it as 1 minus V naught by V in. This V in will get cancelled. So in that case, we will get the expression as Z by 1 minus V naught by V in. So here again V naught by V in is nothing but K we have already assumed. Okay. So that's why Z1 equal to Z by 1 minus K. So the first input impedance we have to derive in this way. And similarly, from the output side to find the output impedance, how we have to take here means the ratio of output voltage to current. To find the input impedance, we have to take the input voltage to the total current. To find the output impedance, we have to take total output voltage divided by total current. So for that purpose, again I am considering the same circuit, but now I am calculating the second impedance Z2 from output to input. We are looking from output to input now. So that's why V naught by I. So again where I value is V naught minus V in now. Why? Because we are looking from output to input. So that's why output voltage first minus input voltage by Z. So Z2 equal to V naught by, substitute this I value. That is Z by V naught by V. Again, in this equation, in the denominator, take V naught common. What we will get? 1 minus V in by V naught. So V naught will get cancelled. We will get it as Z by 1 minus V in by V naught. So what is our K value? K value is V naught by V in. But here we have V in by V naught. So that's why we are representing here it as 1 by K. So overall Z2 is Z divided by 1 minus 1 by K. So if we simplify this, we will get it as Z into K by K minus 1. That is the second impedance. So by using this Miller theorem, we can able to represent the impedance in two poles. So that same Miller's theorem I am going to apply for this hybrid pi model of the common emitter transistor. So this is the hybrid equivalent circuit of the common emitter transistor here with all resistances and conductances and capacitors here. Here we are going to calculate short circuit current gain. So that's why to find the short circuit current gain, I need to short this output terminals. That is VCE should be 0. So once VCE is 0 means these terminals are short circuited. So once these terminals, collector and emitter terminals are short circuited means there is no presence of load resistor RL in the circuit. So after removing this, we will get the equivalent circuit like this. Okay. So from this circuit, we need to calculate the short circuit current gain now. For that purpose, we need to apply the Miller's theorem to the input section as well as to the output section. Okay. So after applying that, we will get the input side these values and in the output side these values. How we got these values? We'll see. So here K value we have assumed it as output voltage by input voltage. Here output voltage is 0. Why? Because output terminals are short circuited. So that's why V naught value is 0. So 0 by V in is 0. So K value is 0 here. Okay. So input side, what are the resistances we are having here? RB dash C divided by 1 minus K. That is we are taking here it as RB dash C only. Why? Because K value is 0 here. So that's why it has RB dash C only. This one, RB dash C. And next two resistances are, we are having RB dash E parallel with RB dash C. But here the RB dash C resistance is very high compared to the RB dash E resistance. Why? Because this resistance will exist in the reverse biased junction and this resistance will exist in the forward biased condition. Always the forward biased junction, the resistance value is very less, but in the reverse biased junction, the resistance value is very high. So if we take two unequal resistances in the parallel combination, means always we will get low resistance as the result. So that's why we will get it as RB dash E here. And two capacitors CE parallel with CC by 1 minus K. So this one we can take it as CE plus CC only. The parallel combination of two capacitors, we will write it as the sum of two capacitances CE plus CC. Why? Because K value is again 0 here. So in this way we got all the parameters in the input side. RB dash C is present and CC by 1 minus K. And at the output side, we are having RB dash C into K by K minus 1. This total value is 0. Why? Because K equal to 0. So, this total RCE will be neglected here. And while coming to the capacitance, we are having CC into K minus 1 by K. So, this can be neglected here. Why? Because the collector capacitor is very less value. So, after applying all that conditions, whatever we derived now, after including all these conditions, our circuit is modified in this way. In the input side only we are having RBB dash resistance and RBE resistance and the sum of two capacitances CE plus CC. And similarly across the output side we don't have any resistances and capacitances, only the output conductance GM is present. So now we need to calculate the current gain value. Okay, so again I am taking the parallel combination of these two. I am indicating here it as the impedance Z. That value is RB dash E parallel with CE plus CC. So these two I am representing it as single impedance. So in that case we will get this particular circuit where Z equal to RB dash E parallel with CE plus CC. So now the current gain is output current by input current, that is load current by base current IB. So from the circuit, IL value we can calculate here it as minus GM VB dash E. Why minus here? Means the load current direction is in this direction but the collector current direction is opposite direction. So that's why we are taking here it as minus GM VB dash E. And what is the VB dash E value? VB dash E value is IB into RB B dash. That is nothing but here not only RB B dash, the total input impedance is present. So that's why IB into Z. So if you substitute this IL value as well as VB dash value in the current gain equation, we will get it as minus GM. Now we will get AI equal to minus GM VB dash E divided by IB. And again in this if we substitute VB dash E value, we will get it as minus GM IBZ divided by IB. So this IB will get cancelled. So current gain GM is equal to minus GM into Z. But what is the value of Z here? The parallel combination of the input resistance as well as sum of all the input capacitances. So substitute that values. So these two parallel combination we can write it as RB dash E into the reactance of these two capacitances XCE plus CC divided by RB dash E plus XCE plus CC. Okay, so this reactance I am writing here it as 1 by J omega form. So after writing this, we will get, and after taking the LCM and simplification, we will get RB dash E divided by 1 plus J omega RB dash E into CE plus CC. Now substitute this Z value here. So after substituting the Z value here, we will get it as this much. So here RB dash E value, we know that HFE by GM here. So from this we can write RB dash E GM is nothing but HFE. So this RB dash E GM value I can replace here it as HFE. So that's why here it is minus HFE divided by 1 plus J omega RB dash E CE plus CC. And again, what's the value of omega here? 2 pi F. After substituting this omega value, we will get it as in the denominator 2 pi F. Okay. And here I am letting the frequency FH value as 1 by 2 pi RB dash E into CE plus CC. So if we include this FH in this equation, we will get it as AA equal to minus HFE divided by 1 plus J into input frequency by FH. So if you find the magnitude of this one, we will get it as determinant of AA equal to HFE under root of 1 plus F by FH whole square. So now we will see the frequency response of the hybrid pi model at different frequencies by using this short circuit current gain formula. Suppose your applied input frequency signal is very less than FH. At that case, what you will get, F value is very less compared to FH means this total denominator value, this value is very less. So root 1 value is 1 only. So that's why this value is HFE. So at F less than FH, the value of gain is HFE. Okay, it is till less than FH, the value is HFE only. When the input signal frequency is equivalent to FH frequency, at that time we will get it as the gain is HFE divided by root 2. That is nothing but here. It is at exact cutoff frequency, exact higher cutoff frequency. But as frequency of the input signal is increasing means the gain value is decreasing here. So that's why we are indicating with a decreasing indication. So this is the frequency versus current gain curve in the case of hybrid pi model of common emitter circuit. So as frequency is varying, the gain value also varying. So from this analysis we can say for the low frequency signals the gain is very high, and as frequency is increasing the gain value also decreasing here, and at cutoff frequencies we will get the moderate gain. Okay, in this session we discussed the different capacitors which are existing in the hybrid pi model and also the short circuit current gain of hybrid pi model, and from that we have seen the analysis of frequency versus gain, how it is varying for different frequencies. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.